Welcome to our Quantum Deep Dive. Today, we're jumping into one of the most, truly, one of the most beautiful and mind-bending ideas in all of science. And we're drawing from a really fantastic essay by Georg O. Schnippot. That's right. Now, you might be thinking, wait a minute, a quantum deep dive? And we're starting with relativity? Well, stick with us, because to really get a grip on the weirdness of the quantum world, you first have to understand the theory that totally flipped our understanding of space and time on its head. Of course, I'm talking about Albert Einstein's General Theory of Relativity.
Okay, so for centuries, right, we all thought of gravity as this mysterious force, an invisible rope pulling things together. But what if that whole idea was just wrong? What if the reason you're sitting in your chair right now isn't because something is pulling you down, but because the very shape of spacetime is holding you there? So, to really get why Einstein's idea was so revolutionary, you've got to go back a bit. We need to talk about the absolute giant on whose shoulders he was standing, Isaac Newton.
And look, for more than 200 years, Newton's theory wasn't just a success. It was basically the law of the cosmos. His math could predict everything from a falling apple to the orbits of planets. It felt like we had it all figured out, Like the universe was this giant, predictable clock, and Newton had given us the instruction manual.
Yeah, almost everything fit perfectly into this neat little picture, except for one little troublemaker, Mercury, the tiny planet zipping around right next to the sun.
See, its orbit was just a little off. It was wobbling, shifting by this tiny, tiny amount that no one could explain, just 43 arc-seconds per century. And okay, an arc-second is 1/3600th of a degree. It's nothing. But for astronomers, this was a huge deal. It was like a typo in the universe's instruction manual. They even made up a whole new planet. They called it Vulcan, just to try and explain the wobble. But no one ever found Vulcan. The mystery just sat there, this little crack in Newton's perfect universe.
And the solution? Well, it didn't come from finding some phantom planet. It came from a total shift in thinking, a completely new way of looking at everything, from a guy working in a patent office in 1915, Albert Einstein.
He started with this amazing thought experiment. He called it his happiest thought. Imagine you're in an elevator with no windows. You feel your feet pressed to the floor. Now, are you sitting on Earth, feeling gravity, or are you way out in deep space, in a rocket that's accelerating upwards? The thing is, there's no experiment you could do inside that box to tell the difference. You just can't. And that right there, that equivalence principle, was the key that unlocked the whole puzzle. If you can't tell the difference between gravity and acceleration, maybe, just maybe, they're the same thing. Maybe gravity isn't a force pulling you down, but is actually the feeling of moving through a universe that's being bent and warped.
Which brings us to this beautiful idea, summed up perfectly by the physicist John Archibald Wheeler. Think of it like this. A massive object like our sun doesn't pull the Earth with some invisible rope. Instead, the sun's immense mass literally creates a dent, a huge curve in the fabric of space-time. And the Earth? It's just rolling along the edge of that dent. It thinks it's going in a straight line, but the line itself is curved. That feeling, that path, that's what we call gravity. It's not a force, it's just geometry.
Okay, so that's a pretty wild idea, but in science, a cool idea isn't enough. You have to be able to prove it. It has to make predictions that you can actually go out and test. And Einstein's theory? It came with a bunch of them.
And boy, did they check out. First up, that annoying wobble in Mercury's orbit, Einstein's math predicted it perfectly, exactly 43 arc-seconds. That crack in Newton's universe was sealed shut. Then, a few years later in 1919, an astronomer named Arthur Eddington used a solar eclipse to watch the light from distant stars. And he saw that as the light passed by the sun, it bent, just as if it were following a curve in space-time. The proof was literally in the stars.
And get this, it's not just space that gets warped, time does too. The theory predicts something called gravitational time dilation. Basically, the stronger the gravity, the slower time ticks. So for the GPS satellites orbiting way up high where gravity is weaker, their clocks actually run a tiny bit faster than ours down here on Earth. The difference is minuscule, just 38 microseconds a day.
So, 38 millionths of a second. Who cares, right? Why does this tiny, tiny number actually matter to you right now?
Oh, it matters a lot. The GPS in your car, on your phone, it needs to be unbelievably precise. And if the engineers didn't program it to correct for that 38 microsecond difference every single day, well, your GPS location would drift by about 10 kilometers every day. It would be completely useless. So yeah, every single time you use Google Maps, you are personally confirming that Einstein was right.
Then, 100 years after Einstein published his theory, we got the most mind-blowing confirmation of all. In 2015, scientists at LIGO heard something. It was the sound of two black holes colliding over 1 billion years ago. But they didn't hear it with a microphone. They detected the literal ripples in space-time, gravitational waves, that washed over the Earth from that ancient collision. We had finally, directly, touched the fabric of space-time itself. It was a total game-changer.
So, with the theory proven over and over, scientists could really start to explore its wildest consequences. And let me tell you, they get pretty strange, and they completely rewrote our story of the cosmos. For instance, general relativity says that if you cram enough matter into a small enough space, you can curve space-time so much that you basically punch a hole in it. A region where the curve is so steep that once you fall in, you can never, ever get out. Not even light can escape. We're talking, of course, about black holes. Every black hole has an event horizon. That's the point of no return. But deep inside, at the very center, the math of general relativity gives us something impossible, a singularity. A point with zero size and infinite density. All our laws of physics just break. They stop working. It's a place where Einstein's beautiful theory hits a wall, and it's basically a giant flashing sign that says, hey, we need a new theory here. And that's where quantum mechanics comes in.
And it wasn't just about weird objects like black holes. When you apply these same equations to the entire universe, they tell you something incredible. They say the universe can't just be sitting there, static. It has to be either expanding or contracting. And that discovery, that simple mathematical result, is the origin of our entire modern cosmology. It's the foundation for the Big Bang Theory.
Which brings us to the biggest puzzle in all physics today. It's the very reason we started this deep dive here. It brings the whole thing full circle. You see, we have these two towering achievements of human intellect: general relativity, which is our rulebook for the very large, planets, stars, galaxies. It's all about smooth, curved space-time. And then we have quantum mechanics, our rulebook for the very small, atoms and particles. And it's all about fuzzy probabilities and chunky, discrete bits of energy. Both theories work perfectly in their own domains. The problem, they absolutely hate each other. Their math is completely incompatible. It's like they're describing two different universes. So, the biggest quest in physics today, the holy grail really, is finding a way to unite them. We need a theory of everything, a theory of quantum gravity. People are working on it, of course. You've probably heard of things like string theory or loop quantum gravity. These are attempts to build a new picture of the universe where space-time itself isn't smooth, but is actually made of tiny, indivisible pixels. If they're right, it could solve all sorts of problems, like what's really going on inside a black hole.
And that's the cliffhanger. That's the profound, unanswered question we're left with. What is the true nature of reality? Is the universe a smooth, continuous fabric like Einstein showed us? Or when you zoom all the way in, does it become a pixelated quantum tapestry? Figuring that out, well, that's going to be the next great scientific revolution. We really hope this deep dive, which we've based on the fantastic work of Jorgo Schneppet, has helped show you how we got to this incredible point in our understanding. Thanks so much for joining us. If you want to dive even deeper, you can find the original essay and more analysis over at schneppet.de. Until next time, goodbye for now.
Schneppet.de is a private project by Jorgo Schneppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.